Dr. Rabul Hussain Laskar from NIT Silchar, and he will be talking on speaker verification, the past, present, and future. Dr. Rabul Hussain Laskar received the BTech degree in Electrical Engineering from Regional Engineering College, Silchar, India. Presently, it is known as NIT Silchar in 1998, and the MTech degree in Signal Processing from the Indian Institute of Technology, Guwahati, in 2007, and the PhD degree in Electronics and Communication Engineering from the National Institute of Technology, Silchar, in 2013. In 1999, he joined the National Institute of Technology, Silchar, as a lecturer in in then Electrical Engineering department. At present, he is working as an associate professor in the Electronics and Communication Engineering from the National Institute of Technology, Silchar. He has more than 19 years of teaching experience, involved in teaching, research, and various other administrative activities in NIT Silchar. His broad area in research includes speech processing, image and video processing, biomedical signal and image processing, machine learning, soft computing techniques, communication engineering, and the other areas related to signal processing. He has more than 70 papers in different reputed journals and 60 international conferences, and around 10 book chapters in image, video, speech, biomedical speech signal processing, and other fields. He has supervised 11 PhD students and supervising another 8 PhD students. He has carrying out 5 sponsored projects by various sponsoring agencies such as BARC, SCRB, etc. and 3 are under review process by SCRB and SPARC. He has supervised 12 PG theses and 1 more is ongoing. He is the reviewer of various international journals and conferences such as Applied Soft Computing, Image Science Journal, Applied Acoustics, Speech Communication, IEEE, Transaction on IEEE, International Informatics, IEEE Access, Neural Computing and Application, Journal of King Saudi University, Journal of Intelligent System, IETE Journal of Research, Signal Processing are few of them. He is involved as TPC members in various conferences such as JIS conference, SPIN, etc. He has research collaboration with IIT Guwahati, IIT Dharwad, NLM, IIT Jaipur, DML University Noida, and various other institutes. Now, may I request you, sir, to kindly start your keynote presentation?
Yeah, sure. So let me make this PPT available. Okay. Yeah, is my PPT visible?
Yes, sir.
Okay, so let me start. Good evening, everyone. And it's my privilege to be a part of this FDP. And at the very outset, I would like to thank Dr. Doreen for inviting me and giving me the opportunity to talk in this particular FDP. So what I thought of is basically discussing about the speaker verification, which is one of my research area. And I thought of giving a brief review for the speaker verification system that has been done for the last at least 20 years by different researchers. And we have also tried to a certain extent a little bit contribution we try to make in this particular direction. So as I'm very much thankful to Mrs. Shakshi for giving a generous introduction about me, and I hope I don't require further introduction after this one. So yeah, myself, Dr. R.H. Laskar, I'm Associate Professor of Department of ECE, and I'll try to give you a brief introduction on the speaker verification for the last 20 years. So here is the outline of my talk. It will start with introduction, and I will try to give you a glimpse about the speaker verification and its application. Then we will try to design a speaker verification system, a baseline speaker verification system, and what are the different performance measures that we will try to look into. And I will try to give you a brief idea about the niche speaker recognition challenge that is organized every alternate years or every year. So that I will try to give you, and some recent trends in the speaker verification system. So next will be the development that we have done at NIT Silchar, but I believe the time will not permit me to show you out some of the results that from our side. So if time permits, I will try to give you some of the information. So that's why I kept it as a separate slide, not included in this particular discussion, in this particular presentation. And finally, some discussion on the state-of-art speaker verification system, and conclusion about the topic, and of course, few references that I have made use for making this particular presentation. So this is a brief outline about the today's topic, that is speaker verification. So let us go ahead. So as you know, that is the speech signal. As such, speech is ubiquitous in nature. That is, it is one of the mode of communication and one of the common mode of communication between the human and human, and it's natural, of course. And this particular speech signal is basically a complex mechanism from production to perception. Basically, if you see this one, that start basically from the brain, which formulate the message, and then this is language coding is done. And this after language coding, what it does is it controls the, neuromuscular construction, and finally this one controls the muscles, and that vocal fold, and that is air pump from the lungs that flows through the vocal folds, and vocal fold control it, and then it flows through the vocal tract, and vocal tract modulate it, basically we can say, and then it comes out from the mouth as a longitudinal pressure variation. Okay, so this longitudinal pressure variation, that is basically captured by our microphone, which acts as a transducer, and this electrical signal, it converts basically a pressure signal wave to a electrical waveform, and this electrical waveform, after sampling and the quantization and of course encoding, is stored in the digital hardware. Okay, so if we go on the other side, there is the perception phenomena. The perception phenomena basically start with the sound that goes into the input of the ear, then basilar membrane, which acts as a frequency analyzer, and then some hair cells, that is what we call the neuromuscular muscles that send the signal to the brain, and the brain does the language decoding and then message decoding, and finally we are able to interpret the message. So this is a brief history, a brief introduction about how the speech production and the perception phenomena goes into, and there are different rates at which this particular signal is processed. So from brain to the, finally to the output of our vocal tract, and similarly on the other side also due to the perception phenomenon. So this is what about the production and the perception phenomenon. But if we look into a speech waveform in a digital hardware, on a digital platform, what we will be going to see is basically an amplitude variation with respect to time. And in this particular amplitude variation with respect to time, what we are calling as the speech signal, it contains a lot of information. The information, what is being said, I mentioned over here, what is being said, that is what message the person is trying to convey. This is one piece of information. The second piece of information is about the language, what language the person is speaking. Third one is who is the speaker, gender of this person, age, emotion. Other than this, the stress level, cognitive load level, depression of the person, is the person sleepy, is the person intoxicated, inebriated, what I have written, is the person intoxicated, that is if he's drunken or not. So all this piece of information is basically embedded in a speech signal. All this, it's nothing like a sandwich kind of stuff. If you think that it's a sandwich, so I will just take out one layer and I will be able to get the speaker information, and another layer I will be able to take the speech information. It's nothing like this. It's amplitude variation with respect to time, and every information is being embedded on this in this particular signal. Okay. For example, on the other day I went to my daughter's school and I was having the wearing masks. So madam was not able to recognize me. Finally, when I spoke to her, and she was able to recognize, oh, you are Rida's father. So that way, she was not able to recognize me by even my physical presence was there, but she was able to identify me from my voice only, or from my speech only. So in that particular signal, even I mean, the other day I was working, doing the exercise, and I was talking to my friend, and he was able to recognize that I was doing something. So that way, even my, I mean, stress level or the cognitive load level is also being recognized, even though you are not being seen, but the person listening to you on the other side from your speech will be able to recognize that, okay, this is condition. So even you have the experience that when you are having cough or something, your voice cracks or voice breaks down. So these are all this information are basically embedded into the speech signal. So basically, I mean, even you may have the experience that when you are talking from a crowded area, so you are, your friend may be telling you that, okay, you speak later on, or it's too noisy, can you repeat, or something like that. So even all this information is basically embedded into the speech signal. And so our objective, what is our objective, is basically that you can see that is, if you look into a speech signal, this will be the nature of the speech signal, that is the time variation, amplitude variation with respect to the time. This is how the speech signal look like. If you plot it on a in any figure or in a digital platform, if you try to look into the signal, it will be like this one. So according to our objective, so what we need to design is basically we want to extract certain type of information from the given speech signal. Maybe what is the message part. So we want to design a system that will be able to identify what message is being conveyed through this particular speech signal. Okay, then if you want to identify the speaker who is speaking, this is what first part is that speech recognition means what is being spoken. So what, and this is speaker recognition means who has spoken. That is you have to identify the person who has spoken this one from the language, from the speech itself. Then similarly, you have the language identification system. We try to design where we want to identify in which language the person is speaking. Then emotion recognition system. The objective is basically to identify the emotion of the person. That is whether he is joy, sorry, angry, I mean what mode he is. So different kind of system target different kind of information, try to extract different kind of information from a given speech signal, and accordingly we try to design a different kind of system. Okay, so you may find the speech recognition, speaker recognition, language identification, emotion recognition, and so many other kind of system that do exist. And everywhere the objective is basically to identify one piece of information or what is the degree of information from the given speech signal. Okay, so in this particular one, so for example, here is how are you. The speech signal looks like in this form. How are you? So a person is speaking, and this one, if you save it in the digital platform, okay, after sampling and quantization and encoding, if you plot the signal, it will look like this one. Okay, so as I was telling you that this particular speech signal contains the message information, it contains the language information. So this message and the language information is basically, we call it the linguistic information. And the speaker, for example, Barun is the speaker, he is in happy mode, that is the emotion recognition, and then it's low cognitive load. So that kind of pieces of information, we basically call it the paralinguistic information. So there are linguistic information, we can say. There is paralinguistic information that is contained in the speech signal, and accordingly each of the system try to make use of one degree of information to design the particular system. So in case of speaker recognition kind of application, which is basically we want to identify the identity of the particular speaker. Okay, so this is what is our objective. That is, we want to identify the we want to extract the speaker specific information from the given speech signal, and accordingly we try to design a system, and this kind of system we call it speaker recognition system. Okay, so we have the speech recognition system, we have the language recognition system, which basically falls into the makes use of the linguistic information in the given speech signal, and we have the speaker recognition, we have the emotion recognition, cognitive load recognition. So, in the speaker recognition, we try to make use of the paralinguistic information from the speech signal, and our objective is to identify who is the person speaking from his or her speech signal. Now, looking into the speaker recognition is basically a broad area. So, if we look into the speaker recognition, it consists of 3 different tasks. And the 3 different tasks are basically, one is basically we can call as the speaker identification. Second task is basically speaker verification, and the third task is speaker diarization. So, we should be able to differentiate between the 3 different tasks under the broad category of the speaker recognition. The speaker identification, the first task, the speaker identification is, for example, let me take an example. You have gone to a class and you want to identify who is Barun, or Barun is present or not. So you know Barun. So what you will be doing is, in a class, if there are 40 students, so you will scan out and you will try to identify the Barun. So it's if there are n students in the class, so it's n is to 1. You are taking n 1 out of n. So it is n is to 1 problem. Whereas in the speaker verification, if I say the speaker verification, all of you, I believe, has the experience of going to the airport. And when you go to the airport, you want to make an entry, you have to stand in front of the security, and security will ask you your identity card. So what he does is basically he looks into your identity card, and to your face, and if this matches, he will allow you to go inside. Otherwise, he will reject you to go inside. So what happens is, it is a 2:1 problem, where if it matches, you will be allowing either one or out of the 2 decisions you have to take. Either you will be accepted or you will be rejected based on the matching between your identity card and your face. So this is a 2:1 problem, we call it, and this is what is basically verification. Whereas when the speaker diarization comes, you can think of a conference scenario where multiple speakers speaking, and you have to say chairman is speaking, and then another member is speaking, then again chairman is speaking. So you want to listen to only chairman, what chairman has spoken. So what you want to do is, you want to isolate when the chairman has spoken these parts, and you want to concatenate, and you want to listen what chairman has spoken over the time. So this kind of stuff is known as basically the speaker diarization. So just a graphical representation of the same is basically, say you are in a speaker identification scenario, you have n number of enrolled speaker into your system, and a person comes and you want to identify who is the person. So what you will do is, you will compare the speech of the unknown speaker with n number of speaker in their speaker model, and what you will do is, you will do the comparison with n number of speaker, and finally the best match with the speaker. For example, it best matches with the speaker number n. So what you will do is, you will be telling that, yeah, the unknown speaker is this particular person. But in case of verification, what happens is, the models are basically stored. Models are stored in the system, and the person comes and he is claiming that I am speaker number 2. So what you will do is, you have already the speaker number 2's template is stored, and the person claims that he is speaker 2. So you will compare between his incoming speech signal with the speaker model 2, and if it is if the likelihood or the match is above certain limit, predefined limit, so you will allow the person or accept the person, or you will reject the claim of that particular person. So this is how the speaker verification works. And as I was talking about the speaker diarization, you can see over there that speaker 1 speaking, speaker 2 speaking, and speaker 3 speaking. So our job is to separate the each of the speaker information from the given recorded signal, speech signal. So this is what is the task speaker diarization. So our objective out here is basically the speaker verification. So if you look into the speaker verification task can be divided into 3 subtasks. And each of them are tasks in their own identity. And one is called basically the text independent speaker verification system. Another is known as the text dependent speaker verification system, and we call the voice password too. So in the text independent system, what happens is basically the speaker need not to remember what he has spoken during the enrollment time. He need not to remember what the text or what the speech he has given during the enrollment time. He need not to remember this particular stuff. And during the testing time, when he is going to access the system, he can make any use of, the speech of his own choice. So there is no dependency. So that's why this kind of system is known as the text independent system. Whereas in the text dependent system, what is required is basically the speaker has to remember what he has told during the enrollment time, and during the testing time, he has to utter the same stuff. Then the system will be able to verify him or identify him. Anyway, in the burst password is similar to the text dependent kind of scenario, but the main difference is basically that in the text dependent scenario, what we do is basically we use 2 to 3 minutes of speech data. For example, a sentence, maybe a sentence kind of stuff. But in case of burst password, what we do is a keyword or a phrase kind of stuff we basically make use of. For example, okay, Google kind of stuff, or maybe some string of numbers or whatever may be. Like the password we make use of in our day-to-day life for accessing computer and other accessories. So this is what is the burst password. So in the text dependent scenario, what is required is you require hours and hours of data for building up the model. And accordingly for testing, you require a minimum of 15 to 30 seconds of data. But now it has been reduced a little bit. But in the text dependent scenario, what is required is you may have a particular phrase, and the speaker during the enrollment will be uttering this particular phrase for a couple of times. And during the testing, he will come and he will utter the same phrase, and the system has to give the access to him or reject the access of him. And the burst password, as I was telling, it may be a keyword. Or, generally, it is less than 1 second of speech that is basically using the burst password kind of scenario. So what happens is in the text dependent scenario, there are 2 actually modes, and in one mode, basically the system prompts the speech signal, and the speaker has to say this particular speech, utter the key phrase. But in case of text non-prompted system, what happens is the system will not be prompting the the phrase. What user has to do is user has to remember and utter the phrase in front of the system. So the text non-prompted kind of system is more preferable as compared to the text prompted kind of system. Anyway, so these are different categories of the speaker verification system. And regarding the application is concerned, is basically there are a lot of applications. For example, nowadays what is happening is basically we use the fingerprint biometric for accessing into the office. Okay, so we can think of replacing that one, that is a system, speech-based system instead of a fingerprint, because in the fingerprint people has to touch some of the device that is kept in a particular location. So this we can avoid. We can have a speech-based system, and what we can do is basically we can design a system, a speech-based system for accessing the office access, for office access, or we can design a system for taking the classroom attendance that may be based on the speech signal. Okay, so this kind of system we can design. Other than this, there are high security applications like mobile banking application where people are targeting for, so biometric authentication for banking or other transactions. So these are high security application kind of scenarios. So here are the 2 examples that I have taken. One is access control to physical system that I have taken from one of the site, but I have not loaded the video because of the time constraint. But those who are interested, you can see the video from this particular site. and you can see the transaction mobile banking kind of scenario that can also be seen in this particular website. Okay, so the video I have not shown over here, but those who are interested, you can check it out and you can see this particular stuff from this website. Anyway, so coming to the, I mean, this is all about the brief introduction about the speaker verification system, and coming to the design of the speaker verification system. The design, I mean, it consists of basically two main units. One we call basically the front end, which takes the speech as the input signal and extract the feature. Feature means what? Some convenient representation of the given speech signal. We call it basically the features. We'll be going to see. Those who don't know, you need not to worry about. We'll go and I'll show you how features are basically extracted. So the front end is basically you have the speech signal as the input. You go and extract the features, which is basically a convenient representation of the speech signal, and that is fed to the backend. And the backend, you have already pre-designed speaker model, and when the speech signal goes in, it will go for it will do the classification and finally decision making, and based on the decision and I mean likelihood and on the pre-designed predetermined threshold, whether the person has to be accepted or rejected, that will be decided by the system. So the input is basically the speech signal, and the output is basically a binary decision whether the person to be given the access or the person has to be rejected. So it consists of, as we have seen, it consists of two modules. One is the front end and another is the back end. Now the challenges comes because of the multiple factors. The factors the design in the I want to mean in the speaker verification system design, the challenges come from many folds. It comes up because of the speaker variability, because I mean we want to mean the session variability, because if you say the word A today and you say the word after 1 month or even after a minute, also the two waveform will be always different. And at certain time, I mean, it's always true. Rather, if you say the word A and if you go on recording the word A 100 times, and if you see the waveform, the no two waveform will be similar at all. So this is what we call basically the session variability. Then there are sensor variability also. Then there are channel variabilities also. So there are multiple factors. The environmental variability also. So all this comes into picture, and that makes the system design a complicated one. Yeah.
Sir, how the channel variation will affect?
Can I take the question at the end?
Channel variation.
Yeah, I'm telling. Can I take the question at the end?
Okay,
Hello?
okay, sir.
Okay. Is it okay now? Up to this? Are you able to understand? Hello?
Yes, sir. Yes, sir.
Okay.
Completely, sir.
Okay. So now, if you go on designing the system, you will see that people are using, for example, in the feature extraction. So people are using different kind of features like MFCC, male frequency capsule coefficient, LFCC, and all these different kind of features people are making use of. But the state of art, the de facto standard is basically the MFCC, the male frequency capsule coefficient, we call it. Okay, and there are also the feature like feedback energies people are now using, of course. And in the classification, people are using DQ, vector quantization, hidden marker model, Gaussian mixer model, maximum likelihood, and Gaussian mixer model UVM up to the DNN people are using. So we'll start with the GMM UVM because this was one of the breakthrough in the area, and we'll start with the GMM UVM and we'll try to go up to the DNN in this particular lecture. And in the channel compensation, that was a question I will try to, give the answer. For example, if you recorded with the with microphone, and if you are now talking in the in a telephonic kind of scenario, so this kind of the channel variability will be there because your enrollment data is from microphone and your testing data is through the mobile phone, or maybe the voice over IP data. So this kind of variabilities, channel variabilities comes into picture. And for channel compensation, what people try to do is or score normalization, people try to do different kind of techniques, J normalization, T normalization, then linear discriminant analysis, I mean, within class covariance normalization, I mean, nuisance attribute projection. So different techniques people are going to, I mean, different kind of technique people has already proposed in this particular domain. So anyway, so let us go ahead and see. We will be, as I told you, we will be trying to design a together, of course, a GMM UBM system, and then from this one will be our starting point, and we will try to go ahead with the current trends, that is the DNN based system. Okay, let's start for designing the system. So in case of designing a particular speaker verification system, what we do is, for example, what is required is basically you can see a UBM model is required, what is known as the universal background model, which is basically a generic model, a speaker independent kind of model. I will show you in details. You need not to worry about. Okay, I will show you in details. So you require a UBM model. Maybe you may have prepared a gender specific UBM, say generic male model and a generic female model. It is not dependent on only speaker or whatever maybe. It is independent of the speaker. And then what you do is basically this UBM is used to design the speaker model. For example, you want to design a official attendance system where you are having 100 staffs. So you may have 100 numbers of people in this particular model. So first model for the first person, second model for the second person, and so on. You design the model, and you have the speaker model. You have the two UBM, one is generic male and another is generic female. So what you do is, when the test data is coming, so for example, the person is claiming I am Ram. So what it will do is, it will extract the feature, and then it will pass through the two paths. One will be comparing with the generic male UBM, and it will determine the level of match with the generic male UBM. And another will be picking up, because Ram's model is already there, so it will pick up the Ram's model, and it will determine the level of match. And what it will do is, then it will compare the likelihood in both the cases, and then it will take the likelihood ratio. And once the likelihood ratio is there, you have a predetermined threshold, and based on the predetermined threshold, if it exceeds that particular threshold, you will allow the speaker to access the system. Otherwise, you will say that not run, you will reject the particular person. So this is how it look like. Okay, so what is required is basically we require a UBM, universal background model, and we require the speaker models. Okay, and these speaker models are basically prepared from the UBM itself, that I will be going to show you out. You need not to worry about. So here is the graphical representation of the same stuff what I was talking about. So you require a generic male model you want to develop. So what you have to do is, you can take n number of speaker, and maybe anything, 1,000, 2,000, 3,000, 10,000. It's I mean it's up to you. So you can take, I mean, the number of speakers. Then there should not be this particular set. That is the second set. That is X1, for which you are going to design the system. That is X1, X2, or Xn are the speaker for which we are going to design the system. So these speakers, that is speaker 1, speaker 2, they need not to be from this particular speakers. They may be different speakers. Okay, and you will be taking n number of speakers, and there are hours and hours of data, and you will extract the feature, and then you will develop a model based on the GMM. For example, in the feature extraction, you are extracting the MFCC feature, and then you will be building up a model using the GMM, and you store it, and you are calling it to be the generic male speaker, male UBM. And then what you can do is, you can similarly take n number of female speaker, and there are hours and hours of data, and you will be extracting the feature. You will be building up a GMM model, and you can call it to be the generic female speaker. Now, when you are going to design the system for the people who are going to access the system, so you will take the speaker 1, his data, say maybe his few minutes of data you will be taking, and what you will be doing is, you will be extracting the feature like MFCC feature. And then what you will be going to do is, this generic male speaker, that UBM you are having, that UBM male will be adopted. That UBM model, that model will be adopted based on this particular data that you are getting from the speaker X1, and this adopted model will be stored as the speaker template in the speaker model. Similarly, what you will be going to do is, you will be taking the speaker X2, you will be extracting the feature, and the generic male speaker, that model you will be trying to adopt to this particular data, and you will be preparing the generics, I mean the speaker model X2 for this particular speaker. So in this way, what you will be trying to do is your generic male or the generic female speaker model, you will be adopting with the data for the speaker who is going to enroll into your system, and you will be preparing a template for this particular speaker and will be storing into your system, and you will be calling it to be the speaker model. Okay. So am I able to make some sense out of this particular one? And hello. So here is a brief. Here's a brief or detailed speaker verification system with different processing units in between. Here you can see that is feature extraction module is there, where we do extract the MFCC feature, and then what we are having is another block that is known as the feature normalization, and then what we are having is speaker modeling. Then model normalization is done, then school normalization, and finally decision making to accept or reject the speaker. Now in the feature extraction, as I have discussed, that we will be going to extract the MFCC kind of feature or other kind of feature people are also using, like PLP feature or filtered bank energies. They will be extracted and they are going to do the feature normalization. So why feature normalization is required? As I told you, there are a lot of variabilities like sensor variability, then channel variability is there. To reduce the this particular effect, people are going to do the feature normalization, and there are different techniques proposed in the literature. Some of them are the capsule mean subtraction related, raster filtering, feature warping, feature mapping. These are some of the techniques. Now, once you build up the model, that is the speaker model, after with the normalized feature, so through GMM, EVM, or different any other model, what you are going to do is you have to do the model normalization. And for model normalization, there are different techniques that do exist: nuisance sensitivity projection, or joint factor analysis, or like LDA, PLDA kind of techniques do exist. And basic objective in this case is basically this model that you prepare, the speaker model that you prepare, do contain the speaker information and the channel information. So if somewhere the other way, if you are able to make the speaker and the channel information orthogonal to each other, orthogonal to each other means you are trying to make them uncorrelated to each other, because if two vectors are orthogonal to each other, then one will not be having a projection on the top of the other. They are basically, correlation is zero. So what you can say is basically, if you are able to make them orthogonal to each other, then you can live out with the speaker information and you can work on the speaker information itself. So this is what is done through the model normalization. And then some technique that is known as the score normalization is basically done. And there are different techniques for the score normalization, like Z normalization and T normalization. The score normalization is something like this. For example, in the in NIT, you are in NIT, so you will be graded in a 0 to 10 scale. And if you are in Assam University, they will be giving the marks in percentage. So what is done is basically, if you want to compare the two guys, in Assam, one from NIT and another from Assam University, so what you have to do is you have to bring their grades or marks in a common scale, and then you can compare them. Okay, so this is what is the job. If you are having the two system, that is one design with the say MFCC and another design with the LPCC or other parameters, and you want to compare the two system. So what you need to do is the score being given by the two system, that has to be taken into a common framework or the common scale, and then you can compare the two system. And then or if you want to fuse the two system together, two different system you want to fuse together to generate a common decision, that is what we call classifier fusion kind of technique. If you want to do so decision level fusion, if you want to do, then what you have to do is you have to do the score normalization. And finally, what you do is basically decision making to accept or reject the speaker. So the decision making, there are soft thresholding, there is hard thresholding, so different techniques are there. So basically we'll try to see later on. Anyway, so what is basically that one, that is the feature extraction. As I was talking to you, for those who are novice in the area, for them, if you look into the speech signal, for example, you have taken a 2 minutes of speech and 2 seconds of speech, 2 seconds of speech, and the speech signal is recorded at 8 kilohertz. So 8,000 into 2 seconds is basically you are having 16,000 sample, and if you take the 16,000 sample together and if you process it, it will be a chaotic kind of situation. The problem is basically the speech signal is non-stationary in nature. And what does non-stationary mean is basically the frequency content of the signal goes on changing over the time. And this kind of signals are basically called the non-stationary signal. So our speech signal or most of the signal that we encountered in nature is basically a non-stationary in nature. So what we need to do is basically we have to because all the theories whatever we are having is basically applicable for the stationary kind of scenarios, but the real signal that are coming, they are basically non-stationary in nature. So what we need to do is we have to make the signal stationary, and then we can apply all the stuffs, that is all the signal processing and all the machine learning tools and techniques we can apply. So what we have to do is we have to segment the signal. It is already observed that if you take a signal from 10 to 30 milliseconds, then the speech signal can be considered to be stationary. For example, if we take the in between, that is 10 to 30 milliseconds, if you take 20 milliseconds a particular one, then 20 milliseconds into 8 kilohertz means that is basically 160 samples. So what we will be taking is 1 to 160. This will be a frame. This many samples will make up one frame. Then what we do is we give 50% overlapping. 50% overlapping means next frame will be starting at 80 and it will be ending at 240. And then third frame will be starting at 160 and it will be ending at 320. So first frame will be 1 to 160, second frame will be 80 sample to 240 sample, third frame will be 160 to 320 sample. So that way we call first frame, second frame, third frame. And if you consider this 160 samples, so what it is experimentally observed is basically the frequency content doesn't change within this particular short span of time, and we can safely assume that the signal is stationary in nature. So for this purpose, the Hamming window is basically used. There are advantages of the Hamming window that I'm not going to discuss over here. And then people do the overlapping as I have discussed, 1 to 160 and then 50 to 80 to again 240. So this is overlapping in nature. The frames are extracted in an overlapping manner. But there are some applications like speech coding where people used to do extract the frames using non-overlapping method. So I mean, here in the speaker verification, we basically extract the frames in an overlapping manner. Okay, that is 1 to 160 the sample, and then 80 to 240 the second frame, then the 160 to 320 will be the third frame, and it will go on. Okay, so the for example here, so you have the frames. And you extracted you fed the frame to the MFCC extractor, that is 1 to 160 sample you have given to the MFCC extractor. So it will extract the MFCC feature, and this MFCC feature, that is 13-dimensional. These are C0, not C1, and so on. These are MFCC coefficients. So 13 MFCC coefficient that makes up a vector. So your 160 samples of the speech signal are now represented with the 13 MFCC coefficient, and this is what is known as the feature vector. So similarly, from the frame 2, you will be extracting the second feature vector. Frame 3, you will be extracting the third feature vector, and so on. If you are having, say, for example, if you take the 2 to 3 seconds of speech signal, you will be getting maximum 250 to 300 in that particular range. Number of frames you will be getting. Okay, giving a 50% overlap that I told you. So this is what you are extracting. So what you are going to do is, that is, you are extracting the feature, MFCC feature, and these are 13-dimensional vectors. And what you are going to do is, for example, if you are having 2 minutes or 3 minutes of speech, then you will be having, say, 30,000 such frames or feature vector. So in a 13-dimensional space, you can now assume in a 13-dimensional space, each of these feature vector will be a point in a 13-dimensional space. So you are having a 13-dimensional space where you are having, say, 30,000 vectors. Okay. So now what is done is basically feature normalization. The feature normalization is done because you have the session variability and all these factors are the sensor variability is there. And to reduce the effect of the session variability and the sensor variability, what is done is basically the feature need to be normalized. For example, here, if you, after extracting the MFCC feature, if you see the distribution of the C0 coefficient out here, then the distribution of the C0 will be an arbitrary distribution. But what is done is basically that arbitrary distribution is mapped to a normal distribution through some techniques, and if you do this particular thing, what you will be going to get is basically that this get is the normalized feature, that is C naught. Similarly, if you take the C1, if you plot the distribution, you will see that the C1 is having a distribution, arbitrary distribution. If you remap it to a normal distribution, then you can get your normalized C1 features and so on. So what you can do is you can normalize the features, and thereby you can reduce the sense of variability and to some extent the session variability to certain extent, and this is what is known as the feature normalization. This is done through mapping the feature through, from an arbitrary distribution to the normal distribution. And there are different other techniques also that I have already mentioned. There are different other techniques. So this is one of the techniques that is basically made use of. Okay, so once you got the normalized feature, what you need to do is the normalized feature, you take the temporal derivative, that is frame 1 minus frame 2, that is frame 1 feature minus frame 2 feature. So you got your first parameter, that is known as the delta parameter. Frame 2 minus frame 3, you got the delta parameter. So in this way you go on doing, you will be getting the first derivative, what is known as the temporal derivative, and this particular feature is known as the delta feature. Then you go on taking the first derivative, you take another temporal derivative. What you will be getting is, that is basically acceleration feature. So you got the feature, and this is known as the delta feature. So what you are having is basically you are having acceleration feature. If you concatenate the, for example, frame 1, that is C0 to Cn, and then D0 to Dn, and N0 to M. So you will be getting a feature vector that will be a 13 into 3, that is 39-dimensional feature, a 39-dimensional feature vector, and which includes the temporal derivative also into account. So so this is what is known as the MFCC and delta feature. This is what is known as the MFCC and delta feature. So this is what we make use of. And then once you are having the feature, what you have to do is you have to go for the modeling. And in the GMM framework is basically, for example, you are now having 39-dimensional space where you are having 30,000 or 40,000 or 50,000 points in a 39-dimensional space. So visualization is basically very difficult. So for just the visualization here, I have shown a 2-dimensional space where C0 and C1 are the 2 dimensions. C0 and C1 are the 2 dimensions. And I have populated all the, if we populate it, what we can show is they forms a cluster in the 2-dimensional space. And you can imagine that this particular cluster can be represented by one Gaussian. This particular cluster can be represented by another Gaussian. Okay, so this is what visualization in a 2-dimensional space is quite easy. But if you assume that you are having a 39-dimensional space and there you are having 50,000 points, so visualization is really very difficult. So let us try to see in a 2-dimensional space how we do the modeling. For example, in a 39-dimensional space, your data is distributed and follows a particular kind of distribution. And let's try to visualize the same in a 2-dimensional space. For example, this is a kind of arbitrary distribution in a 2-dimensional space. And say this red arbitrary distributed PDF can be modeled by 3 Gaussians, as you can see, one in the green color, another is in the violet color, and another with the pink color. And if each of the Gaussian will be having its mean and the variance and the weight. And if you give the appropriate mean, variance, and the weight to each of the Gaussians and add them up together, and then you will be you will be able to estimate the PDF overall PDF. So this particular concept is known as the Gaussian mixture model, and this is basically used in building the model, GMM model. So it should be remembered that all the weights that you are assigning to each of the Gaussian should be equal to 1. So what is required is each of the Gaussian has to have a mean, and variance and the weight. So I mean, if I have 10 Gaussians, so 10 means 10 weight and 10 variances that will be required to approximate the probability distribution overall PDM. So now, as any system you are going to design, what is required is basically you require a training set to build up the UVM model. You require the target set for which you are going to design the system, and a test set for testing or validate the system. So what here I have given a typical example. For example, 56 male speaker. Each speaker is having 2 minutes of speech for creating the UBM, and 20 male speaker for which you are going to design the system. So you will be having each speaker 2 minutes of speech. So this is how with this you will be building up the speaker specific model, and then for testing you may have 250 male speaker. There may be imposter also for testing the system. So if you see the standard database, they call it basically the background set. For this training set, and for the target set they call it development set, and for test set they call it basically the evaluation set. For example, if you take the RSR 215 data, so they will be calling it the background set, they are calling it the development set and the evaluation set. Okay, so this is about the database. Anyway, if you have the database, so what you are going to do is you will be building up the UBM. What is basically UBM? It is basically the GMM that I just told you. You will be preparing the GMM, that is the mean variance, and the weight you will be capturing for independent of the speaker. For example, you develop a GMM model with 1024, UBM model with 1024 Gaussians. We call it mixture, 1024 mixture. Okay, so here is the red ones are say the Gaussians. This is the first Gaussian. This is the second Gaussian, this is the 998 Gaussian, and this is the 1024 Gaussian. Now what you will be doing is, for example, your speaker 1, you are trying to enroll into the system. So what you will do is, these cross are basically the speaker 1's data. So when the speaker 1 data is projected on the UVM, what we observe is basically that the cross are falling well into the first Gaussian. But if you see in the second Gaussian, no cross is falling. But if you take the 998 Gaussian, some of the cross are inside, some of the cross are outside. If you take the 1024 Gaussian, some of the cross are inside, some of the cross are outside the Gaussian. So what we do is, what the adaptation will do, model adaptation will do is, it will adjust the 998 Gaussian, this red Gaussian, it will adapt it in such a way to feed the distribution of the speaker 1's data. Similarly, it will feed it will adopt the 1024 Gaussian to feed the speaker 1's data. So in that way, what it will do is, it will adapt the mean and variance of all the Gaussians to feed the data of the first speaker that you want to enroll into the system. And accordingly, what you will be getting is, you will be getting the adapted mean, adapted weights, adapted variance, and this is what is your speaker model 1. So you will go on doing this, and you will be getting the speaker model 1 for your system. So what is required is, as you can see in this particular, for example, it is your X1 speaker that you want to enroll into the system. You have a UBM model ready. So what you will be doing is, you will be adapting the mixtures, and accordingly for mixture 1, you will be having a weight, you will be having a mean, and you will be having a variance. You can see the dimension I have mentioned over here. And similarly for mixture 2, you will be having weight, mean, and variance. And for 1024 mixture, that is 14024 number of Gaussian, you will be having a mean, variance, and the weight. So if you see that for a particular speaker, that is the first speaker for developing the system, for our first speaker X1, what is required is, you have to store a 1 by 1024 weight vector. You have to store a 39 by 1024 mean matrix, as you can see over there, 39 by 1024, because I have selected 1024 Gaussians. 1024 number of Gaussian are required to model the distribution of the X1 speaker. So that is why 1024. So similarly, you have to store a covariance matrix of 39 by 1024 for speaker model 1. Similarly, I have to do the same things for speaker model 2. I have to do the same things for speaker model M. So I will be getting all the speaker model. So you can see for each of the speaker, what I have to store is basically a vector and 2 matrices. One is the mean matrix, another is the covariance matrix that I need to store. And similarly, I have to do for all the speakers in the system. Okay, to build up my speaker model. Okay. Now the problem is basically that in the GMM UBM model, so a lot of metrics and vectors need to be stored, and people thought of, okay, why not? I mean, it can be why not? It can be done with a single vector, okay, for corresponding to a particular speaker. So what they did was that all the means that you are getting, that is 39 into 1024, said all the mean vector, all the mean, this mean 39 by 1 mean 39. The next 39, next 39, all the means are basically concatenated together, and they are getting a 39 into 1024 vector. and this particular vector, they are basically scaled with the weight and the covariance matrix, that weight and the covariance matrix, and they are getting a single vector, and they are calling it to be the super vector. So you are getting a 39 by 1024 mean vector that is basically normalized by weight and the covariance, and you are getting a single vector. You are calling it to be a super vector. And now, instead of storing all the pieces of information, what you need to do is you have to store a single vector corresponding to each of the speaker, and that is what is known as the super vector you need to store for each of. So each of the speaker will be having one vector, super vector, and super vector for each of the speaker you need to store. And this is a very popular concept, super vector, and how to construct the super vector. That is that I tried to show over here. Anyway, because of the time, I am not able to go in detail. Anyway, so what we are going to do is, once the super vector is there, as you can see, the super vector is of dimension 39 into 1024. Okay, even though it is a single vector, but its dimension is very large. 39 into 1024 turns out to be 39,000 something. Okay, so it's a very lengthy vector. So people observe this particular vector, and they have seen that it consists of this particular vector. That super vector consists of basically the speaker information, as well as the channel information and some residual component, then some speaker independent component. So they try to make use of a concept known as the joint factor analysis, and they try to decompose this particular vector into different component. One is the speaker independent component, another is speaker dependent component, another is a channel dependent component, another is speaker dependent residual component. And this y out here, this is very much important. And this vector y, this is a vector, and b is a matrix. And this y component out here is very much important. And it is observed that this contains all the speaker specific information. So people made use of this particular y to design the system. And this is particular modeling technique is known as the joint factor analysis model. And then people thought of that, okay, we can do a little bit better. What they do is basically they used to decompose this particular one, that is the super vector, using another technique known as the I vector space modeling, and or known as the total variability matrix. This T matrix out here, that is n plus T into W, this is known as the total variability matrix into W. And this particular W, it is observed that this W, it contains all the speaker specific information. As you can see, this W follows a normal distribution with some mean and some variance, and this mean is basically the desired I vector. So what they did was, instead of working with all the stuff, speaker, channel, and every information, they try to decompose it, and they try to take out the mean information, and they play with that particular W information, and they try to play with this one. And this is what is known as the I vector concept. And even today, the I vector is one of the dominating technique in the speaker verification. Okay, so let us have a graphical look into, or pictorial look into how this I vectors are derived. So if you are having f is the feature dimension, for example 39, and if you are having say a number of frames, so what you will be doing is this frames will be converted into f, that is the 39. And if you are having C, that is 1024 mixture of Gaussian, so you will be getting a matrix of 39 into 1024 matrix. And this 39 into 1024 matrix will be concatenated. This means all the means will be concatenated to make up a 39 into 1024 length vector. And finally, this vector, which what we are calling as a super vector, will be decomposed into a matrix, that is T matrix, F into C, that is the into R, where R is the rank of the matrix. This is what is the T matrix, and there is a term W coming, and this W will be R into 1, and that R into 1 is basically R into 1 W, that is will be a vector, and this vector is basically your I vector. So this I vector is basically very important, and it is considered to be one of the state-of-art technique. And even today, if you develop a particular system, and you have to compare your system with the I vector framework. Okay. So then comes the model normalization. There are different techniques for the model normalization. As I told you, it consists of both the speaker and the channel information, and you have to remove the make them orthogonal to each other. That is the speaker and channel, or you have to make it orthogonal. And if you are able to make it orthogonal, then you can play with the speaker specific information, and you can design your system and you can get a better system out of it. And there are different techniques do exist in this particular domain. Out of this, basically the PLDA is now dominating kind of technique that is people are using nowadays. And I told you there is the score normalization, because as I told you, when you want to compare two systems may be generating the score in two different scales. So what you need to do is you have to take them in the common scale, and then accordingly what you need to do is you can either compare the system as I have shown over there. You can see if you are having two system design, say this is designed using the I-vector technique, this system is designed using GMM UVM, this system is designed using the say DNN, and if you compare the three system, so what you have to do is you have to do the score normalization, and then you can compare the system. Or otherwise what you can do is, if you want to fuse the system, that is decision level fusion, if you want to do, so say this fusion is done by through a neural network, what you have to do is you have to normalize the score, and once you normalize the score, you can feed it to the neural network for the fusion of the decision level fusion technique of the different systems. So this is what you can do. And for decision making, what I have already shown you, you have to compute the likelihood scores, if whether it comes from the speaker model, by the what is the likelihood with respect to the UVM, and then you take the log, and this is what is known as the log likelihood, LLR, log likelihood ratio, LLR, and we denote it by L. If L is less than or equal to a predetermined threshold, then we reject the speaker, and if it is above this particular threshold, predetermined threshold, then we accept the speaker. I'll talk about how this particular theta is being selected. I'll come to this one, and this is basically the speaker normalization I just told you. Okay, so now how to capture this particular value theta? How to capture this particular theta? Because you want to make a decision whether the person is to be accepted or whether the person has to be rejected. So for this purpose, you have to make a decision. Okay, you require a threshold against which you will be comparing the scores that is being generated. So what we do is, if you look into this particular table, what is, if you have the true speaker, and this is if you consider the true speaker is correctly identified by your system, so this is your correct decision. If the true speaker is rejected by the system, so this is the miss. If the imposter is accepted by your system, then your system is making an error, so this is what is known as the false acceptance. And if the imposter is rejected by your system is making a correct decision. So two correct decisions are there, and in one case the true speaker is rejected by the system, and the other case your imposter is basically accepted by your system. This is a mistake your system is doing. So what we basically do is, what if you look into this particular one, so true speaker is correctly accepted, imposter rejected, so it's a correct decision. True speaker is rejected by the system, this is miss, and imposter is accepted by the system, so this is a false acceptance. So if you test your system, okay, so true speaker as well as the say some imposter, and what you do is, if you record that how many times your system has rejected the true speaker, that is the miss, and how many times your system has accepted the false speaker, that is imposter. So what you can do is, in terms of percentage, if you calculate it, if you plot the false acceptance along the x-axis and the miss one along the y-axis, and if for a particular value of theta, so what you will be getting is, you will be getting a point in this particular two-dimensional space, and if you plot it, this is the point with the yellow dot out here. Now if you go on vary your threshold, that is the theta, and then I mean miss and the false acceptance, that will go on, it will change, and you will be getting a second point out there, say somewhere out there. And if you go on changing the value of theta, so what, and you will be getting the points, a lot of points in this particular two-dimensional space, and if you join them together, what you will be getting is, you will be getting a curve, and this particular curve is known as the detection error threshold curve. So what this particular curve is saying you, for example, if you are on the yellow dot, so what is happening is, your miss rate is very high, but your false acceptance is very low. What does it mean is, basically your system is basically rejecting the true speaker quite good amount of time, but less number of imposter is allowed by your system. So what is basically your system is doing is, your system is basically a high security kind of system. Okay, your system is basically a high security kind of system. So this kind of system is preferable. So this is what you are getting for, because you selected a value of theta in such a way that the miss rate will be very high. That is, the true speaker will be rejected multiple times by the system, whereas the false speaker may not be rejected by. So it's basically inconvenience for the true speaker, but your system is not allowing any, very less number of false speaker. So this kind of scenario is basically suitable for banking application. But if you see the other end of that particular DET curve, what is happening out there is you can see your false acceptance is very high. That is, your imposters are easily allowed by the system, whereas your true acceptance rate is very low. That is, the true speaker is not missed by the system. Okay, true speaker are also allowed, and imposters are also being allowed by the system. So this is happening because you have decided a threshold somewhere out here in this particular region. Okay, so this particular threshold, this is maybe a very inconvenient kind of scenario for a convenient kind of scenario, and this kind of system what you can make use for low security applications. Here is an example. You can see I have showed here, if you select this particular region of operation in this particular zone, that is the theta you select to operate in this particular region, it will be a high security kind of stuff. If you select this particular your theta in such a way to operate in this particular region in your DET curve, it will be high convenience region. So this is low security area, whereas this part is a high security area. And a point in this particular curve where your miss rate and the false acceptance rate are equal, this particular point is known as the equal error rate. This particular point, a threshold, a theta, for which the miss rate and the false acceptance rate are equal, this is known as the equal error rate. Okay, so this is the point where we generally operate our system. Now, so what we say is our system is having a ER of 1%. So this means what? That is the 1% times is the miss rate, and 1% is the false acceptance rate. Okay. So if I design, let's say, 3 systems, and 3 system is having 3 different DET curve, and they are having 3 different equal error rates. So as I go down, you can see the ER rate is going. If I join all the points, then it will be falling into on the line y equal to x. That is all the points, ER points. If I just join, it will be falling on the y equal to x line. So if I go down towards the origin, this I will be getting a better and better system. And if I go up toward y equal to x line, the systems are not going to be better. For example, in this situation, my third system is better than the other 2 systems. That is because it is providing me the less equal error rate. Okay, so this is all about that how we evaluate the performance of the system. Okay, so regarding the the niche speaker evaluation that started in 96 basically, and as you can see, it is basically conducted in alternate 2 years or alternate years, and it is continuously going on. And what they do basically is, as you can see, it is going up to 2020, 2021 maybe there. Okay, so what they do is they used to provide you the previous data to build up your background model, and then what you do is they will be providing the new data in the challenge for designing your speaker specific model and testing the model. So you can design your model and you can participate in the process, and they will evaluate your system performance of your system, and accordingly they rank the different institute based on the performance of their system. I remember that in 2011 IIT participated, and in that competition they stood to be 11, and Brahma University they stood the first. So here is for example the call for 2020. You can see that the next evaluation is currently planned for fall 2020. Click here for details. So you can see that they are providing you the database for they are provided for developing the system, and then for validation you can participate with your system, and and you can demonstrate your system, and accordingly they will evaluate the performance and they will grade you out. Okay, so this is the system. This is what the competition goes on. If you have the system, you can go ahead with this particular competition. Now coming to the discussion, what we have done is basically what we have extracted the MFCC plus delta feature from the speech signal. Then we have the UVM model we tried to develop, and then we adapted the UVM through map adaptation. Map adaptation means maximum a posteriori probability adaptation, and then we developed the speaker specific GMM model, and then we try to compute the likelihood, and then based on the likelihood and the predetermined threshold, we accept the or reject the speaker. Okay, so now the next thing is basically that GMM requires a lot of data, mean, covariance, and the weight to be stored. So people what they try to do was they try to extract the super vector, and it is observed that the super vector is a single vector and it is independent of the duration of the speech. Okay, because now it is 39 into 1024, 39 is the dimension of the feature and 1024 is the number of mixture. So it is the duration, how many frames are there, this is immaterial. Also, it is independent of the length of the speech signal. Okay, now what they did was they introduced the SVM scoring, and then through the SVM scoring, they try to accept the reject the speaker. So then what the people did is basically they use the super vector, and in 2005 they use the super vector, and then they use the nuisance attribute projection. That is what they tried to do. Did was some channel effect they try to reduce, and then they apply the same SVM scoring technique that is already existing, and they try to develop the system. So they introduce the nuisance attribute projection in between to reduce the channel effect from the super vector. Finally, what they did was they came up with the joint vector analysis in between. After extracting the super vector, so they did the joint vector analysis, and they take the y vector as I have shown already, and then instead of that NAP, nuisance attribute projection, they use the concept known as the within class covariance normalization to reduce the session variability, and then they use the SVM scoring to accept or reject the speaker. And thereby, as you can see, that when the super vector was 39,936 dimension, and this particular y vector, that is after joint vector analysis, this is of dimension only 400. So now you are having a length of 400, vector of length 400 need to be stored rather than the 39,936 length vector. So this is what people are doing in 2007. And then came the, of course, the I vector in 2009. So what happens is people made use of the, instead of y vector, that is the joint vector analysis, they use the total variability matrix, and they extracted the I vector, and then what they do was within class covariance normalization, that is done already out here in 2007, and then they use a technique known as the Lda projection. The Lda is that's to reduce the dimension of the I vector. They use the Lda projection. That is they are retaining the most significant dimension of the speaker specific information, and then they are instead of SVM scoring out there in 2007, in 2009 they use the cosine distance scoring, okay, to accept or reject the speaker. And cosine distance, you know, that is the angle between the two vectors gives the similarity. If they are orthogonal to each other, then there is no similarity, but if one is overlapping on the top of the other, then it is the maximum similarity, and the cosine distance scoring is able to give this piece of information. Okay, so what they did was, instead of this WCNN and the Lda, what they tried to did was they use the PLDA technique, probabilistic linear discriminant analysis technique, and in that particular technique in 2009. What they have shown is that is the I vector space can be decomposed into two spaces. One is the channel space, another subspace, another is the speaker subspace. And if you are able to decompose into two spaces, the I vector space into two spaces, then you can work with the speaker space and you can design your system. So what they did was they take the speaker space, they compute the likelihood, log likelihood ratio, and based on this they used to accept or reject the speaker. So this is what is basically the best solution that was existing till 2009-2010 in the speaker verification scenario. Then came the DNN framework, and with the DNN framework in 2010 it started, but this I vector framework was considered to be the baseline system for any comparison that you are making. So in the DNN framework, what the people I am having only 30 minutes time, so I'll be trying to rush to that DNN kind of stuff. So what they try to do is there are two different approach philosophies in the DNN-based speaker verification or recognition system. One approach is basically can we have the alternative to that particular I vector? Can we have that feature? That vector is to be captured by the DNN. So this is one of the stuff that is in one direction. And another thing is basically, as I have written over here, you can see, use the deep learning for classification and decision making, like replacing your PLDA, cosine distance scoring, and all this kind of stuff. So these are the two different philosophies. And in this particular case, basically the first one is leading till now. I don't know what will happen in the future, but the first approach is leading till now. That is alternative to the I vector people are trying for. So, I mean, people try to make use of, the bottleneck feature, and one of the very important work that was done by, this Google group, and they proposed the D vector kind of framework, and this D vector is nothing but an alternative to the I vector, and that D vector was captured by the deep neural network. What they did was they fed the deep neural network with the stacked filter bank energies. Instead of MFCCs, they are using the filter bank energies as the input, and then there are hidden layers, and then finally a softmax layer. And in the softmax layer, you have the speaker 1, speaker 2, speaker n, and so on at the output. And what they are doing is they're training this particular system for speaker identification, and for speaker verification. What they are doing is basically they are after that network is being trained. So the softmax layer was taken out, and the last layer, average activation from the last hidden layer, that was what they were using, and the dimension of this particular last layer was D, so they are calling it to be the D vector. And this D vector, average activation of from the last layer, they are using as a D vector, and that is basically used in substitute to that particular I vector, as I was telling, as a substitute to that particular I vector framework. And that is what they did on the OK Google database, and they reported that the performance was very close to the I vector framework. As you can see, 1.21% a year for I vector and 2.00 for the D vector framework. Then in 2015, that another system came up, and they have shown that when the speaker is speaking a particular phrase, for example, in a text-dependent kind of scenarios, the speaker is all the speakers are asked to say one picture is better than 1,000 words. So all the speakers are basically asked to say. So it is observed that if a particular speaker speak a phrase, then the style, then other emphasis to be given in different words, syllables, and all for phonemes, that changes from speaker to speaker. So what they tried to do was they tried to train the system corresponding to speaker and the phrase together, and this is what is known as the multitask learning framework. That is speaker, first phrase, first speaker, second phrase, first speaker, third phrase, then speaker 2, first phrase 1, speaker 2, phrase 2, and so on. They tried to develop the system in that way. And what they did was after similar to the D vector, and after the last layer, average activation of the last layer, they were extract, and they used they named that particular vector as the J vector, known as the joint vector. And when they used it in the PLD and the cosine distance measure, after that, by replacing the I vector with the J vector, they observed that this particular system was able to give a better performance in the RSR 215 database for text-dependent speaker verification scenario, where D vector was providing 21.05% a year. This particular system was providing 9.85% a year. So then this is a very important paper in 2018-19. This particular paper is very much important, and it is considered to be the state-of-art technique in the speaker verification. This particular concept is known as the X vector concept. So because of the time constraint, it's not possible for me to discuss in detail, but I would suggest my audience to go through this particular paper. This is considered to be the recent state-of-art paper in this particular domain, and this is known as the based on speaker embedding or DNN embedding, speaker embedding technique. And they are using this particular network as the time delay network, and they are also using the temporal context that known as the temporal contexting. They are also using the context of local contexting, and then what they are doing is they're introducing the statistical pooling and affine transformation. Basically, what they are trying to do in this particular stuff was they are trying to do the speaker verification through speaker identification. It was a speaker identity. It seems to be a speaker identification, but what they are doing is basically it was basically speaker verification through speaker identification. So this paper was this particular concept was proposed in 1989 by Hinton and their group, but it didn't become popular at that point of time. But what happened in 2018-19, it was basically once again revived, and this particular concept was used in speaker verification task, and it was it was providing the best performance. What they did was, after that time delay neural network in this particular layer, they are using the statistical pooling technique, and then they are using the affine transform, and from the embedding A, they are extracting the feature. That is what they are trying to call the X vector. From the embedding A, they are that embedding A, the feature at this layer, they are considering it to be the X vector, and this is what uses substitute to the I vector. And it is surprising to observe that ER was reduced drastically, and it was beating the that one, that is the I vector based system. Okay, so this was what they have done in 1819. Then the Google came up with one of the end-to-end system, and this is also DNN and LSTM based system. What they did was they use, for example, you want to design the system with this particular model. What you need to do is you have to go to the system, and you require the enrollment data. So say you are telling, okay, Google 10 times. So what it will do is it will build up a DNN model for you, and as you know, the D vector that I just spoken, it will extract the D vector and from the 10 utterances, and it will store a template for you. Similarly, when you go for the evaluation, you will be speaking the same thing, okay, Google, and then system will extract the D vector, and it will compare through cosine similarity and do the logistic regression, and finally accept or reject you. And this DNN was basically replaced with the LSTM, and it is observed that LSTM performs better than the DNN based system. So this is from Google, and they are calling it to be the end-to-end system. Okay, so what happens then? People came up with the deep belief network, and this is the architecture of the deep belief network. And what you can see is basically the deep belief network is basically trained with the stacked RBM model, stacked RBM. And what it is observed is basically that it has not been tested with a standard database like RSS or other kind of databases, like niche databases. It has been tested on Lda database, and it was shown that, okay, when you extract these hidden layer features from the DBN and combine with MFCC feature, this combined DBN alone, DBN feature cannot beat the MFCC I vector based system. But if you extract the DBN feature, and if you combine it with MFCC feature, and then you go for the I vector extraction, and then do the PLDA scoring and cosine distance scoring, then this kind of system provide a performance better than the standalone MFCC based feature. So this is what they reported. And finally, then the second philosophy, that is based on deep learning for classification, people came out with variational autoencoder. So this is what I am just skipping out because of the time constraint. And then people came out with multi-domain feature. That is what they are trying to do is they are trying to develop an automatic speech recognition system, and here is a speaker recognition engine. So what they are trying to do is they are extracting the phone posterior from the speaker recognition speech recognition system. They are feeding it to the input to the speech recognition system, and in that way it's vice versa. That is, they are extracting the information from the speaker specific information, and they are feeding it to the speech recognition engine. So that's why it is known as the multi-domain feature. That is, the two feature from two different domains are basically fed into one task. So this one they are doing, and they have observed that if they are doing in that way, then this multitask method provide better performance than the standalone I vector based system. And that has been done on WSG database. That was not done on the NIST SRE or other kind of database. And then this is basically 2017 paper came in 2018, and this is one of the technique that uses the DBN, deep belief network. And in this case, they are like UBM. They are designing an UDBN, that is universal deep belief network. They are designing, and what they are doing is they are having this DBN is designed using the background I vector. And what they are doing is they are having the target I vector, and that DBN, the universal DBN, is basically adapted. And for adaptation, they are using a special balance training technique for adapting the DBN corresponding to a target speaker. And then what they are doing is that adapted feature, whatever they are getting, with this they are training a DNN with the target speaker I vector as well as the imposter speaker I vector. And what they are trying to do is, in that case, they are developing a feature vector in such a way that should have very good discriminating property of the target speaker. So what they are doing is they are storing it in the model, and when the unknown I vector is coming, they are comparing the resemblance, and accordingly they are making a decision. So this is a transaction paper that came in 18, and it was worth reading. But what it is observed is this particular system, as you can see, this particular system was not able to provide a better performance as compared to the I vector framework. It's almost equivalent performance that has been noticed in this particular system. Okay, so but fusing of DNN approach and the PLDA, that revealed better performance. That is what they reported. Anyway, so this was one of the very good paper. And next paper, the next concept that was introduced is basically SyncNet, that was introduced by Yoshua Bengio and his group. And that was basically, I like this particular concept because this was basically from signal processing perspective. And they are basically just try to revive the end-to-end system. In the end-to-end system, the first up to this CNN, DNN, that is basically capturing the filters information. But what happens is basically in their case, what they do is basically, say, for example, in case of MFCC, we have the MFCC filters. Each of the filter is predefined. But in this case, they are asking the network to learn the filters, and not the whole filter like previous cases, the end-to-end system. They are not asking the the network to learn whole the filter. Rather, only the lower cutoff and the higher cutoff frequency of the filter is basically learned. And they consider the filter to be sync filters, and therefore the name of the network is basically SyncNet. And then once the filter is being captured, they feed it to the CNN DNN layer, and then finally softmax layer for the speaker classification. And for speaker verification, what they did was they extract the feature from the last layer, and that is put into the PLDA and the cosine distance framework. And what they observed is basically that this particular system was able to provide a performance that is on TMIT database. The result was basically comparable to the I vector based framework. Okay, so what happened then? People came out with different other models, I'm running short of time, I think. So what people came out with the hybrid framework, then the curriculum learning also technique. The people proposed curriculum learning technique also. People proposed. Then hybrid learning based also technique. That is HMM DNN framework. People try to propose, and we also did some work in this particular direction. Okay. So anyway, so this is up to 2018-19, and 2020. Basically, if you see the computer speech language processing, and you will there is a recent special what we call special topic, and in the special topic, the speaker verification was one of the topic, and that lead of the guest editor was Douglas Rayland, who is the father of the speaker verification, we can say, and is from MIT lab, who is the person who designed the GMM UVM framework. Okay, so what in this particular one in 2021, so new speaker embedding technique like XPECT, or what we have discussed, speaker embedding technique like ResNet BAM, that is the residual net ResNet with bottleneck attention module. So this is they are calling as the ResNet BAM. This has been proposed to further improve the representation power of the ResNet. And then the snap-based deep speaker network with cosine similarity spoofing has also been proposed. Then two-stream synchronization convolution neural network with audio-visual data has also been based on audio-visual data has also been proposed. Then for spoofing attack, for anti-spoofing, basically spoof detection, deep generative variational auto-encoding based technique has also been proposed. Okay, so and various other models are proposed. I have taken few of the models which are basically I believe is worth enough. So I mean, so finally coming to the conclusion. So what we have observed is that the speaker verification that started in long back 1960s, and it started with spectrogram and simple template based matching. And in 96 onward, the NIST was conducting regular formal speaker verification evaluation, and they provide the common experimental framework and corpora for developing your system and verifying your system. And in doing so, they are providing us the latest speaker recognition technology. And today we are having computing resources, big data, and we are having, I mean, artificial neural networks. Okay, so with this, the NIST is basically focusing on more realistic speaker in the world scenarios. Okay, so so in the 2 decades of systematic and open competition evaluation that has been done by the NIST, and it is demonstrated that the speaker recognition is basically a reliable and testable technology for person authentication with growing commercial and security application. Okay, so 2 decades of speaker recognition and evaluation we have seen, and now the question is, are we yet there? The answer may be both yes and no. It is apparent that the speaker recognition technology has been seen the significant advancements in the last 2 decades, and the channel variation and the domain mismatch has been addressed to great extent. The state-of-art system has increased capability to deal with shorter segments, enrollment segment also, like I have shown the OK Google kind of scenario. So it's able to handle the shorter segment, test segment also. Moreover, we have witnessed successful deployment of the speaker recognition technology in commercial products, which has been possible through the effective techniques such as data augmentation, speaker modeling techniques like I-vector, and speaker embedding technique like X-vector based techniques, then different score normalization technique, as well as the fusion techniques. What remains as open challenge is basically the interplay between the factorization of text, that is what I call the message, and the speaker characteristics. So this one, the factorization still remain a challenging issue. In addition to this end-to-end modeling for speaker recognition, audio-visual, that is multimodal speaker recognition, as well as the voice biometric security, like I have shown the spoofing attack and all. So this has been driving the field forward in the future. And what we have observed is the DLS deep learning has become a state-of-art solution, both in speaker verification and identification. And the standard X-vector, in addition to the I-vector, are nowadays used as the baseline for most of the novel work. But with the increasing amount of data, and we are having the deep learning architectures, powerful deep learning architectures. So I believe in future, newer deep learning architectures will be developed that can lead a breakthrough in the speaker recognition technology. So with this, these are some of the references that I have made use of for preparing this presentation. And I'm sorry that I am not able to show you out what we have done at NIT Silchar. If we get the opportunity in near future, I will try to show you what we have done at NIT Silchar. Okay. So thank you all. Thank you for listening. Okay. Thank you, sir.
Okay, so thank you for your wonderful talk, Dr. Rahul Hussain Laskar. And is there any question from the audience participants? Just let's take some 1 or 2 questions because we are running short of time. Any questions from the participants? Sakshi, are you there?
Yes, sir.
Okay.
Okay. Thank you so much, sir, for your wonderful presentation. We get to know a lot about speech recognition and speaker verification. And thank you, participants, for making the workshop amazing. And we'll meet tomorrow at 1 p.m.
Thank you. Thank you all. Bye-bye.
Okay, bye. Good night. So let's meet tomorrow at 1 o'clock for the 5th day FDP program.